Hello class, our next lesson is on section 2.6, which is forced oscillations and resonance. So this uses undamped forced oscillations. So for us to study those undamped oscillations under the influence of the external force, f of t is equal to f sub 0 times the cosine of omega t. We begin with the equation m times x double prime plus kx is equal to f sub 0 times the cosine of omega t, whose complementary function is x sub c is equal to c sub 1 times the cosine of omega sub 0 times t plus c sub 2 times the sine of omega sub 0 times t, with omega sub 0 being the square root of k over m as the circular natural frequency of the mass spring system. The corresponding frequency is V is equal to omega divided by 2 pi hertz. Initially assuming the external and natural frequencies are unequal, so omega is not the same as omega sub 0, we would substitute x sub p is equal to a cosine of omega t to find a particular solution. So this would then yield negative m times omega squared times a times the cosine of omega t plus k times a times the cosine of omega t plus f sub 0 times the cosine of omega t, where a is f sub 0 over k minus m times omega squared, so that being f sub 0 divided by m, divided by omega sub 0 squared minus omega squared. Thus, x sub p of t is f sub 0 divided by m divided by omega sub 0 squared minus omega squared times the cosine of omega t. The general solution being the complementary solution x sub c plus the particular x sub p is x of t is equal to c sub 1 times the cosine of omega t plus c sub 2 times the sine of omega t plus f sub 0 divided by m divided by omega sub 0 squared minus omega squared times the cosine of omega t. This being c times the cosine of omega sub 0 times t minus alpha plus f sub 0 divided by m divided by omega sub 0 squared minus omega squared times the cosine of omega t. And one such example of that is this cart with flywheel system, giving our initial position, equilibrium position, k being the spring constant there, x being this distance, and we have our different values according to that. So let's say, for example, that m is 1, k is 9, f sub 0 is 80, omega is 5. The differential equation would then be x double prime plus 9x is equal to 80 times the cosine of 5t. We want x of t of x of 0 and x prime of 0 are both 0. So the natural frequency from this is omega sub 0, that being equal to the square root of 9, so 3 in this case. But that is not the value of omega, which we were given to be 5, which is our frequency. So we could use what we just saw on that last screen. So here, we want to substitute x sub p is equal to a times the cosine of 5t. So putting that into a differential equation, we would get negative 25 times a plus 9a is equal to 80, which means that a is negative 5. So a particular solution would be x sub p of t is negative 5 times the cosine of 5t. So the complementary function would be x sub c is c sub 1 times the cosine of 3t plus c sub 2 times the sine of 3t. The general solution for that non-homogeneous equation is going to be x of t is c sub 1 times the cosine of 3t plus c sub 2 times the sine of 3t minus 5 times the cosine of 5t. And we know from this that x prime of t is going to be negative 3 times c sub 1 times the sine of 3t plus 3 times c sub 2 times the cosine of 3t plus 25 times the sine of 5t. So, the initial conditions, so from x of 0 and x prime of 0 both being 0, we would obtain that c sub 1 is 5, c sub 2 is 0. So the particular solution, the one that we desired, going to be x of t is 5 times the cosine of 3t minus 5 times the cosine of 5t. And the period for this is 2 pi, which is the least common multiple of 2 pi over 3 and 2 pi over 5 from our cosine terms, which gives us that value of 2 pi. So with beats, the imposing initial conditions x of 0 is equal to x prime of 0 is 0 yields c sub 1 is equal to f sub 0 divided by m times omega sub 0 squared minus omega squared, and c sub 2 is 0. So the particular solution is x of t is equal to f sub 0 divided by m times omega sub 0 squared minus omega squared times the cosine of omega t minus the cosine of omega sub 0 times t. From those trigonometric identities, x of t would be 2 times f sub 0 divided by m times omega sub 0 squared minus omega squared times the sine of a half times omega sub 0 minus omega t times the sine of 1/2 times omega sub 0 plus omega times t. Or we could write x of t being a of t times sine of 1/2 times omega sub 0 plus omega times t, with amplitude a of t is equal to 2 times f sub 0 divided by m times omega sub 0 squared minus omega squared times the sine of 1/2 times omega sub 0 minus omega times t. A rapid oscillation with a comparatively slowly varying periodic amplitude exhibits beats. So this idea of resonance, we can express the amplitude as A is equal to f sub 0 divided by k minus m times omega squared, that being f sub 0 divided by k divided by 1 minus omega divided by omega sub 0 squared. This being positive and negative rho times f sub 0 over k. F sub 0 over k is the static displacement of a spring with constant k due to a constant force f sub 0. and amplification factor rho being 1 over the absolute value of 1 minus omega divided by omega sub 0 squared. Resonance is where the increase without bound as omega approaches omega sub 0 and the amplitude of oscillations of an undamped system with natural frequency omega sub 0 in response to an external force with frequency omega being approximately omega sub 0. If these were equal, the oscillations would increase without bound. So for example 2, we want to suppose m is 5 kilograms, k is 500 newtons per meter. In the cart with the flywheel, we want to find the natural frequency. So that will be omega sub 0, being that natural frequency. This gives us the square root of k over m. So square root of 500 divided by 5, that made the square root of 100, which is 10 radians per second. And the frequency is 10 over 2 pi, which is about 1.59 hertz. For this, we would expect oscillations with large amplitude if the flywheel revolves at that frequency of 1.59, multiply that by 60 seconds per minute for 95 revolutions per minute. So when we model the mechanical system, this is where we have the principle of the conservation of energy is useful, using the following kinetic and potential energy formulas. So 2 kinetic and 2 potential. First kinetic energy, T, capital T is 1/2 mv squared for a translation of mass m with velocity v. And capital T is 1/2 of I times omega squared for rotation of a body of movement of inertia I with angular velocity omega. Potential energy, we have capital V is 1/2 k times x squared for a spring with constant k stretched or compressed at distance x. And capital V is equal to m times g times h for the gravitational potential energy m, gravitational potential energy of mass m at a height h above the reference level, v being 0, provided that g, the gravitational constant, may be essentially constant. So that's example 3. Find the natural frequency of a mass m on a spring with constant k if, instead of sliding without friction, it is a uniform disk of radius a that rolls without slipping. So being denoted here in this picture over here. So from that principle of the conservation of energy, we can write our differential equation here, or at least part of it here, as 1/2 times mv squared plus 1/2 times I times omega squared plus 1/2 times kx squared. And this being equal to E. Here, E is the total mechanical energy of the system. of the system. And this is a constant. So for this, we know, so let us let V be A times omega and I to be MA squared over 2, because this is a uniform circular disk. So we can simplify our equation to be 3/4 times mv squared plus a half kx squared is equal to E. And that's supposed to be an E, not a K. So we want to differentiate now with respect to T. With respect to T. So in this particular case, we would have V is X prime and V prime is X double prime. So this would give us, this would yield 3/2 times M X prime times X double prime plus K X times X prime is equal to 0. But if we divide and simplify, so divide by 3/2 times M, we then get the following simplified form. X double prime plus 2K over 3M times X is equal to 0. So we divide by 3/2 M X prime to get that. So the natural frequency from that back and forth motion is the square root of 2K over 3M. That being the square root of 2/3, which is approximately 0.8165 times the natural frequency. So for example 4, I have suppose a car oscillates vertically as if it were a mass. M is 800 kilograms on a single spring with constant K being 7 times 10 to the 4th newtons per meter attached to a single dash pot with constant C being 3,000 newtons, 3,000 newtons times seconds divided by meters. Suppose this car with the dash pot disconnected is driven along a washboard's road surface with an amplitude of 5 centimeters and a wavelength of L being 10 meters. At what car speed will resonance vibrations occur? So for this, we are going to say that this is a unicycle. So we are going to let X of t be the upward displacement of mass m from equilibrium position equilibrium position, we're going to ignore gravity. So the equation of the road surface is going to be y is equal to a times the cosine of 2 pi s divided by L, with a being 0.05 meters and L being 10 meters. So the car in motion causes the spring to be stretched by x minus y from that Newton's second law of motion. We can write that mx double prime is equal to negative k times x minus y. Or we could just write that simply as mx double prime plus kx is equal to ky. We are going to let v be the velocity of the car. So for this, s would be equal to v times t. Then we can rewrite this as mx double prime plus kx is equal to ka times the cosine of 2 pi vt over L. And this describes the vertical oscillations of the car. Okay. So the forced oscillations occur with circular frequency omega being 2 pi v over L. The resonance occurs at omega being omega sub 0 being the square root of k over m. So the speed of the car of resonance this should be v is L over 2 pi times the square root of k over m. So in our case, 10 over 2 pi times the square root of, this should be 7 times 10 to the 4th divided by 800. Tossing the calculation to a calculator gives us about 14.89 meters per second. So now the damped forced oscillations, this is real physical systems, always have some damping, such as friction. Complementary function x sub c of m times x double prime plus c x prime plus kx is equal to f sub 0 times the cosine of omega t approaches 0 as t approaches infinity. Thus, x sub c is a transient solution that dies out with the passage of time, leaving the particular solution x sub p. So, by the method of undetermined coefficients, we yield the steady periodic oscillation x sub p of t is equal to c times the cosine of omega t minus alpha, has amplitude c is equal to the square root of a squared plus b squared, that being f sub 0 divided by the square root of k minus m times omega squared plus c times omega squared. But sine of alpha is b over c, that's greater than 0. So tangent of alpha is b over a, c times omega divided by k minus m times omega squared. Alpha would be between 0 and pi. So alpha is inverse tangent of c times omega over k minus m times omega squared if k is greater than m times omega squared, or pi plus inverse tangent of c times omega divided by k minus m times omega squared if k is less than m times omega squared. So for example 5 here, I have defined the transient motion and steady periodic oscillations of a damped mass and spring system where m is 1, c is 2, k is 26. Under the influence of an external force, f of t is 82 times the cosine of 4t, x of 0 is 6, x prime of 0 is 0, and we want to investigate the possibility of practical resonance for this system. So the motion, the resultant motion, is going to be x of t is x sub tr of t, this is the transient motion, plus x sub sp of t, this being the steady periodic oscillation. So the initial value problem that we're going to have for this is going to be x double prime plus 2x prime plus 26 times x is equal to 82 times the cosine of 4t, with x of 0 being 6 and x prime of 0 being 0. So from this, we have a characteristic equation. R squared plus 2r plus 26. And well, this factors slightly to be r plus 1 squared plus 25 is equal to 0. So from this, we have our roots to be negative 1 plus and minus 5i. So from this, our complementary function would be x sub c of t is e to the negative t times c sub 1 times the cosine of 5t plus c sub 2 times the sine of 5t. So we could guess the solution to be x of t is a times the cosine of 4t plus b times the sine of 4t. If we substitute this into a differential equation with our various forms in here, we would get 10a plus 8b is equal to 82 and negative 8a plus 10b is equal to 0. From these, a is 5, b is 4. So our general solution would take the form of this being x of t is e to the negative t times c sub 1 times the cosine of 5t plus c sub 2 times the sine of 5t plus 5 times the cosine of 4t plus 4 times the sine of 4t. So based on the initial conditions, c sub 1 would be 1, c sub 2 is 3. So the transient motion would be x sub tr of t. This is e to the negative t times the cosine of 5t minus 3 times the sine of 5t. That steady periodic oscillation y sub sp of t is 5 times the cosine of 4t plus 4 times the sine of 4t. So this can be written as the square root of 41 times 5 over the square root of 41 times the cosine of 4t plus 4 over the square root of 41 times the sine of 4t. And this can be written as the square root of 41 times the cosine of 4t minus alpha. And this is where alpha is the inverse tangent of 4/5. If we put that into a calculator, we get about 0.6747. Okay, so I need to erase a little bit here so we could go look at the resonance portion now. Okay, so the forced amplitude of frequency omega omega. We could write that as C of omega is eta2 divided by the square root of 676 minus 48 times omega squared. That's supposed to be a squared. plus omega to the fourth. That whole thing. So maximum amplitude occurs when we have C prime of omega being equal to, this would be, once we do this, this would be negative 41 is 4 times omega cubed minus 96 times omega divided by 676 minus 48 times omega squared plus omega to the fourth raised to the 3/2 power. And we could kind of, well, try to anyway, make that a little bit nicer. That's negative 164 times omega times omega squared minus 24 divided by 676 minus 48 times omega squared plus omega to the fourth to the 3/2 power. We would set that be equaling to 0. So when it comes to that practical resonance, this happens with external frequency being omega is the square root of 24. And this is indeed less than a value for omega sub 0 for that critical frequency being the square root of 26. Let me know if you have any questions or concerns. Thank you.